Yeah, so we're the time series group working with anomaly detection in heart rate data. And we're Kasper, who's, well, he's here, but on Zoom. It's me, Erik, it's Peng from Lund, and Michele from WASP-UU, and also Selma. And yeah, people not from Lund and WASP-UU, from Chalmers, all of us. And this heart rate data that we've been working on is an example of time series. Okay. And a time series, yes, mathematically, is just a sequence of observations, right, indexed by time. There are plenty of examples of time series. For instance, financial data, time series data. So this, I think, is like some kind of index closing each day. Daily temperature, for instance, is another example of a time series, or in our case, heart rate data, so from this electrical signal from the heart. And there are various things you can want to do with a time series, right? You might want to do some kind of prediction, predict what's going to happen in the future. You might want to extract some kind of seasonality to say, well, how does the time series vary over time? You might want to extract some trend. And a lot of approaches from this in statistics are built on taking historical data and then fitting a time series model, which sometimes confusingly also is called a time series. But this is just in a sequence of stochastic or random variables that should somehow, if you do your modeling work well, capture the observed data points. And then if you have that, you can do, you can do your predictions, you can do your trend extraction or whatever you want to do. But in this project, as hinted by the title, we want to do something called anomaly detection, meaning that given some historical time series, if we get a new time series, can we say if this time series is the same type? Is it a representative of what we have seen historically? And our approach that we're going to take doesn't really require us to do a time series modeling. So it's in a sense data-based, right? We just take data and we learn something, and that's going to help us to solve a problem. And to do this, we are going to use autoencoders. And what are autoencoders? Well, an autoencoder consists of two neural networks. We have an encoder that's going to map you into some latent space or learn a representation of your time series. We're going to have a decoder that maps you back into the time series space. And the autoencoder is trained to reconstruct data well. So you feed it some examples and you train it on how well it can actually map into the latent space and then reconstruct from the latent space using the second. So it minimizes this similarity score. And the idea then is that if you train it on a written normal time series, it learns to reconstruct normal time series well. So the idea then is that if it maps something in that is anomalous, or just, you can observe it, it's different what we train it on, into the autoencoder, it shouldn't really be able to reconstruct it, because the autoencoder should learn these sort of large-scale structures in the data, and if those are not present, it should just output some nonsense. So you should be able to detect it if something is anomalous or different or strange. And the autoencoders we use, these neural networks, are, in the context of this project, you can make very fancy autoencoders. In our project, they aren't really very fancy, it's just linear networks, simple networks, not that deep, not that large. They map into a 10-dimensional latent space. So nothing really fancy, but it works well enough for our purposes. And now, yeah, and as I said, we train this based comparing the decoder and the structure. And this worked rather well. But I said we're going to use this for heart rate data, which has these sort of common large-scale structures, if you're healthy. And if you're unhealthy, which we're trying to detect here, your heart rate is going to be different. And that is Selma.
Yes, so we decided to use heart rate data, or more specifically, electrocardiogram or ECG data. These are recordings of the electrical activity of the heart, or more specifically, they are graphs or time series where you have the voltage on the y-axis and the x-axis, and they are measured by placing these small electrodes on the skin. You can use them to diagnose various heart conditions, such as arrhythmia, which means that you have a regular heartbeat, or ischemia, I think that means that the blood flow to your heart is restricted, or other abnormalities. And they are generally identified by looking at the ECG and comparing them to like the standard pattern. So if you see a deviation, it's probably some kind of heart condition. So why did we decide to use this approach with autoencoders for this type of data? So first of all, this kind of data is routinely collected at hospitals, which means that at least in theory, there would be an abundance of data, which we can use to train our machine learning models on. Moreover, this kind of data is it's very structured and repeated. So all the healthy ECGs, as you see here, would have more or less the same shape. But the anomalous ECGs will have very different shape from the normal ones, and they can also be different to each other depending on the heart condition. And this is very good for an autoencoder since they exceed at kind of learning this normal pattern. Meaning that if we use only the healthy data when we train our autoencoder, it will struggle to reconstruct the unhealthy ECG data, which you can see here, for example, in this figure. And then we can identify that this is probably an anomaly. We use the ECG 5000 dataset. This dataset is derived from another dataset, which consists of this very long-term ECG recordings, as you can see here on this figure. And they are based on recordings from 15 different patients, 11 men and 4 women of different ages. And then there has been performed some pre-processing, and this is what the ECG 5000 data is. So the pre-processing consisted of 3 different steps. Basically, the first one is to actually extract the heartbeats of these very long recordings. Second one is to adjust the length of each heartbeat using interpolation, so they each have the same length of 140 time steps. And finally, they sampled at random 5,000 heartbeats. And this data set is annotated. So we have 2,079 healthy heartbeats, and we have 2,921 anomalous heartbeats. And actually, these anomalous heartbeats are categorized into 4 different categories depending on what kind of heart condition the patient has. But for our purposes, we decided to just group all the anomalous time series into one category. And this is basically because of 2 main reasons. The first one is it's simpler, especially for our autoencoder approach. And the second reason is it kind of more is in line with how this would be used in real life medical healthcare. We want like an alert system that alerts the physicians that, okay, something's wrong. It's not so interesting to know exactly what kind of heart condition the patient has. The most important thing is to just alert the physician so they can come and further examine the patient.
Yeah, so I'm going to talk about how to actually detect anomalies using autoencoders. And for the moment, just imagine that we are working with one single autoencoder and with only one huge data set. So the core idea of the autoencoder is that it is trained on normal healthy ECGs, which means that it is supposed to capture the core information contained in the healthy patient's data set. which is basically summarized by the 10 encoded features or by general data representation, which is then fed to the decoder, which outputs a reconstructed time series. So there's an input time series and an output time series. And we compare these two using a suitable metric or similarity score. For our purposes, we chose to use the standard MSE loss, but we could have used other loss functions for if we are in context of time series, such as dynamic time warping. So once the autoencoder is trained on normal healthy patients, you can actually apply the autoencoder on the same data set that is used on the training step, which is composed of normal healthy ECGs, and compute a collection of reconstruction losses, which is the way in which we compare the input of the autoencoder with the final output of the autoencoder. And then approximate the distribution of these reconstruction losses using the CDF. And this is how we actually use this to detect anomalies. So we feed normal time series into the autoencoder, and we build and we estimate the distribution of the reconstruction losses on the training data. And then after we have computed the ECDF, we can choose a suitable cutoff of this ECDF to detect anomalies. So the core idea here is that if the autoencoder is fed a normal time series, then the corresponding reconstruction loss should not be an outlier with respect to the distribution of the reconstruction losses on the normal healthy ECGs. Instead, if it is fed an anomalous ECG, it will output something completely different, and therefore the reconstruction loss will be highly different once we train. That's the underlying assumption. So this item is supposed to summarize kind of the terminology that we use in the report, just to make it simple for you to actually read the report. So with this terminology D, we basically mean the MSE loss between the training the healthy ECG Z and the reconstructed ECG. And we use a very short notation to talk about this in the report. And pi d is supposed to represent the distribution, the relative distribution of these reconstruction losses on the training data. And this is the final output of each of our kind of model pipeline. A single number between 0 and 1 is actually a probability, which is supposed to kind of be interpreted as the probability or chance that the given time series is actually an anomaly or not. So the way in which this probability is defined is, of course, based on the CDF, but it kind of relates to the concept of p-value. So we kind of reject or we claim that the point where time series is an anomaly if the probability of observing a training reconstruction loss higher than the amount that actually observed is small. So the underlying assumption of this entire thing is that the shape of normal signals is highly different than the shape of anomalous signals, because we are basing everything on the reconstruction loss. So this is an example in which this procedure will not work. So I'm not going to details about what this data actually is. The important thing is that green is normal signals, red are anomalies. And as you can see, the anomalies are kind of different with respect to the normal signals, but not that much, meaning that the reconstruction loss on anomalous signals will not be an outlier with respect to the distribution of the healthy data. Yeah, now Kasper will share the screen.
All right. Can you hear me?
Yes.
Yes, great. Let's see. All right. So now we turn our attention towards the main purpose behind this project, scalability. So what my collaborators here has presented is this main idea of what we're actually proposing to do, this anomaly detection for this ECG data. But how do we scale this? We believe this idea is a good idea, and we want to just do an ensemble of this model over different nodes to scale with the data, essentially. So The main thing is that let's see, if the data is large enough or too big for a single machine to handle, we simply want to employ the data on different machines, different nodes. So that's like the main idea behind the ensemble. And what this enables is the application of a distributed framework in general, which can gives acceleration during training if we find an efficient point of partitioning the data. We could also allow for respecting privacy of data at the local machines. If we have hospital data from different hospitals, they can keep their own data and train on this at each node, essentially. We also have quite low transfer cost, especially during inference. So in the end, when we do this anomaly detection, these different nodes will only have to return the anomaly score back to this master node. But we will go through a more detailed version of this now. So if we assume we have some data set D with some size, SD, and we also know that each machine can handle at most S1 data points within a reasonable time frame. So that means that we can learn a model. A model can be learned on at most S1 data points in a time that we find feasible. So the idea here is that we will use this ensemble approach if this data set is larger than S1. Otherwise, we would perhaps stick to a single machine if that's increases our performance. So if the data set is too big, we will partition it into n chunks. They can be of different sizes, but the largest has to be smaller than S1 essentially. And then we distribute the n chunks to n nodes. So we use the same number of nodes as we do in the distribution. And during inference, this system becomes quite fault tolerance functional because essentially if one node fails, we still get the anomaly detection score from all the other nodes. And we believe each node will be trained quite similarly to each other, since we will assume this partition of data is IID over the different nodes. It's a super simple idea. It scales very easily. So as the data set grows, we can just add additional nodes arbitrarily, as long as our cluster supports this to maintain a similar performance. So what we do in practice is that during training, we let each node receive their data chunk, and this happens in parallel, of course. So that's some sort of okay. So we have two cases. So if the nodes already have their data, we don't have to really send out the data. Otherwise, we have a one-to-all communication here by sending out the different data chunks. Then each node defines their model, and each model is then trained on the respective data until some convergence or some criteria is met, and we are happy with the training. And then at inference time, we get some data set, d-test, that we want to perform the anomaly detection on. This could be a single time series or it could be a large set. And if we assume this data set is smaller than S1, we send the whole data set to each node. So once again, some sort of one-to-all communication. But if it's larger than S1, we would have to partition it and send a bit at a time. And then each node evaluates and returns the anomaly score, which is, of course, very cheap transfer cost. And the anomaly score, of course, is this CDF that Michele talked about. And then the master nodes, so each node returns this score to the master node, which computes the mean. And that's the end output of the inference cycle, essentially. So to summarize this pipeline, we have in green down to the left this training cycle where we partition the data and set each part to a node, and we learn a corresponding model. And then at inference, in red, we get some time series that we want to perform anomaly detection on. We send it to each of the nodes, and each of them outputs a deviation score. And this score is then sent to the master node, which outputs the mean, for example, or some weighted average. But in our case, we all have only used the mean. And And now Peng will talk a bit more about how we employ this in practice in our code. You need to share as well on Zoom for the recording.
So a real-world scenario we came up with for this approach is we have a centralized healthcare management system like 1177 in Sweden. So imagine you have the nation's patient records of 10 years. So it's too big to fit in a single node at 1177. Although vertical scaling is possible, but on the other hand, hospitals, they do have infrastructure there, and sometimes they could be idle, so they are available. Or it could simply cost 1177 too much to upgrade their infrastructure. So the better option is actually they act as a master or driver here to distribute the training job to these hospitals. Also, it has the power to prescribe that each hospital only trains the model with the data set, they have access to, which is the patient's data who has registered with that hospital. So to again preserves the patient's privacy. And the benefit of this approach is that also all the hospitals eventually can have access to this shared model after aggregation. So the underlying, we use this touch distributor library as some of the groups did as well. Our approach only used perhaps half of the potential of it. Another aspect of its scalability is enabled by this distributed data parallel mechanism. So after you create different processes, this process can actually communicate with the other about the gradients and synchronize their parameters as well. But for our problem, we only used half of its scalability, which is distribute the training by dividing the data set to different workloads. And here is the main function to initiate this pipeline. Here again, it actually shows the pretty beauty of this library because it's very simple and very brief. So what you needed to do is only to create this touch distributor instance and give some parameters to specify numbers of processes, like how many workloads you want to involve. Local mode is the toggle to whether you want to have the driver or master node to be involved in the training job. And you can also switch between GPU and a regular CPU. And after that, you just call this run function. And the function there is the training, or can be a Python script you give it to. And the arguments other hyperparameters you want to specify, for example, number of epochs and learning rate, etc. Here we also briefly touch a little bit upon our collaboration environment setup. So we also use the Docker because we have very heterogeneous devices. So it's we want to prevent like inconsistent dependency or code conflicts. So what we have done is we have adopted this official PySpark Docker image, and on top of that, we installed the PyTorch, and the torch distributor is native to PySpark, and we just push it to everyone's machine locally, and then they write their code in this container. Afterwards, they just push their code to GitHub. So it streamlines the workflow for our collaboration. Now we'll talk about the results.
Yeah, we talk about the results. So some practicalities, we decided to split our list into 9 chunks, and each node receives 1 chunk and is trained on that chunk. So for this entire thing to work, we have to have that each model is trained properly. What we've done is we have, of course, created a test data set composed of some normal and some abnormal ECGs, and then we've tested the performance of each individual of 9 models on this test data. So as you can see here, the first five, we have gathered 1,000 new ECGs. The first 5,000 are normal ECGs, and the last 5,000 are anomalies. And as you can see, all the models here kind of assign a high anomaly score in the last 5,000 test points, and also some of the 500 anomalies, time series. And in the report, we've also summarized this with proper precision or performance metrics. I'm not going to bother with details here, but the point is that each model works effectively if we select a suitably high threshold. And of course, and then all this, the results of all these models is aggregated by simply averaging over all these anomaly scores. And this is the result of the entire ensemble. So on the right, you see the anomaly probabilities ensembled using the results of all the 9 models, and similar comments could be made for the performance of this ensemble. So yeah, that's the end of the presentation. We are ready for the session. Thank you.
So I was curious, so you're looking at classifying anomalies from normal ECGs versus sort of doesn't actually. Did you look at the latent specifications? Like, did you consider that for participation, like clustering or something?
Yeah, we did. We did. And there are people who try to do that, but the thing is, the latent representation is it's not real, right? I mean, it's a 10-dimensional vector space, and then each model will learn different features, right, and assign them to different places in this 10-dimensional vector space. So they're artificial in some sense. So how would you compare these artificial vector spaces that are very depending on the training between different models? So in those methods, it's not clear to us exactly how they would be made scalable, for instance. But if you do, however, use the construction back in your time series space, there we have a sort of shared space between all the different models, which is sort of has a clear interpretation. It's the space of time series.
Yeah, that's interesting. I always forget that things change when you work in distribution.
More of a basic question. Which your axis here is the predicted and which is the actual? Because there's one of the mistakes where it's 0 and 1 where it's like 43. So is it confusing normal ECGs for anomalous or anomalous ECGs for normals?
The plot on the right,
Yes, on the confusion matrix. Yes.
Oh, left. We took the plot on the right, we set the threshold, and all the numbers above the threshold were selected as anomalies.
Yeah.
Yeah, and so the axes are here, so anomalous, normal.
Yes, but which of them are the actual and which of them is the predicted? So is the model confusing normal for anomalous, or is the model confusing anomalous for normal?
Yeah, very good point. So these are the y-axis are the predicted. Yeah.
Okay.
Yeah, sorry. Yeah, very good point.
So it's confusing normal.
Yeah. Yes. Because some of these points here are have a anomaly score which is higher than the threshold, and therefore it's
Alright, so it's, I guess, false positives then instead of false negatives.
yeah.
And actually, we used a bit of, or I did, because I made a figure. It's a bit of this figure here is a bit of false marketing. So actually, this distribution of empirical scores has a really long tail.
Yeah.
Because at some point, there's been some kind of doctor sat down and classified is this normal or not, right? And probably if you would look at them, they would look kind of strange, compared to, but still, it's fine, doctor. But really, it goes on quite a while.
Yeah.
But you have this bulk here. Yeah, this gamma looking distribution thing, and then you have a couple of points far to the right here.
Yeah, I mean, so I guess
Those are
better,
probably classified.
yeah, I mean, better a false positive in this case than a false negative.
Probably.
I just find some of the math stats a bit confusing. But it's okay, high level, an autoencoder is essentially an approximation of an identity function for a set of elements, right? So that's what you have. And so, I mean, I like these cutoff things, it makes sense, it's used in the industry a lot. But in this example, right, you will always have to pick a cutoff, which means it's also reflecting the approximation error in your ID, right? So what I would like to somehow see is that some kind of validation holdout, to actually make the autoencoders justifiable, right? That it's not like, because if I make the nodes really big, I can just approximate everything, right? And if I make it small, the big space will be too small. So there is basically some kind of hyperparameter tuning that I feel is missing, right? Because you don't have like held out validation data to make sure that you don't right? You know what I mean? Overtrain or undertrain. I think if that's fixed, then all of the other things make statistical sense, right?
I mean, we have kind of decided the number of included features based on holding out some of the healthy patients and non-healthy patients that compared to the final.
Oh, okay.
But that was not a rigorous parameter search because for each choice of latent representation, we have to train everything for each node. But yeah, a rigorous approach would be much better.
Yeah.
Justify the choice.
But you don't have to pick a cut, right? You could say this is so confident or mild list, right? It's 0.94.
Yeah, but you still have to somehow, like the whole learning theory justification of model selection is sort of off without that's what I'm over. But the other question I had was, in the ensemble setting, like you have all these models, but are they technically they can be arbitrary architectures or whatever. So all you expect is these small hospital provide a score. So, yeah.
So with the data, like in real life, really like half the anomalous and half the normal, I would kind of imagine that more are normal. Yeah, but like, so that because should that affect kind of like how you should, because you tested them half, and I assume you train with the data set which has more.
No, the training doesn't see any anomalies.
They didn't see any anomalies.
So there's the technical part.
Yeah.
And I think the example we had at the time series that doesn't work is a pretty. You can't do this with something that's too similar to do that. And we had this picture, right? It's a visualization of the latent space. Yeah. Right? So this is just PCA, right? The first few components. So we do really see kind of that you get to clusters, right? But with the data we had, let's see this one. If you do the same thing there, you really just get two superimposed graphs. So There's limitations.
Follow-up question. I mean, it would be interesting to see just this sort of the false negatives and false positives with the actual distribution of healthy and non healthy, just to see how.
Oh yeah, we had that, but it looks very different. So you get this sort of gamma looking thing with this long tail, and then you have like this spike basically out to the right. So it's not too interesting. I can't tell you.
Okay, if there are no other questions, let's thank them again.